So hello, this is Galen Pickett again from Cal State Long Beach. This is Physics 151, and today I want to talk about Chapter 8. And the interesting idea about Chapter 8 is that the internal energy in a system, for a real physical system that's good with the quantum energy principle, there are particular energies that are available inside the system, although the energy principle overall is still the guiding principle for how energy can come into the system or out of the system. So here's what I want to talk about, the quantum energy principle. So here I've got a potential energy, which is the same potential energy of interaction you would have for a macroscopic spring. So I got a spring, it has a spring constant K, and if I did not put a tension on this end, this free end would snap right back here. So it's got a natural size of 0. So x is equal to 0 here, and you can go outwards. The potential energy of the spring would increase. But in a quantum system, it is not true that you can have any old energy that you want. So you cannot have this energy, and in fact you can't have this energy right here. If you had this state where you had the spring was at rest at the origin, then you would know where the particle is exactly. You know, it's at the origin, and you would know how fast it's going. You'd know exactly what its momentum is. And there is a fundamental relationship, the uncertainty in your position times the uncertainty in your momentum. This comes from a quantum mechanics point of view, is greater than or equal to h bar over 2. There is a fundamental limit on how well you can know a state, which means that there's going to be a lowest energy which is not at rest. And there it is right there. In terms of the properties of the spring, K is a spring constant, M is the mass, so this is a frequency squared, so I take the square root of that, I get a frequency times h bar. That is this whole quantity here. This h bar times the square root of K over M has units of energy. I'm going to call that epsilon naught. So the possible energies are 1/2 this natural energy of the spring, and then to get the next one, you can add E0 to it, and you can add E0 to the next one. So you had this ladder of separate spaces. So if you try to do work from the surroundings, so you try to put a particular amount of energy in delta E, and that can be in the form of a photon coming into the system, photon with that energy. If the system starts in the ground state and your delta E is like so, the photon can come in, but there is no way for that delta E to be accommodated by the internal structure of the system. So the photon comes in and then it goes out. The only thing it can do is elastic. If that photon energy is tuned to be exactly one of these epsilons, then you can have the photon comes in, this state starts off at this bottommost energy, the energy comes in, and now you've changed the internal energy of the system. That is an inelastic process. So we've changed the internal energy of the system. The energy principle is still true. The change in the internal energy of the system is equal to the work from the surroundings. This work from the surroundings is the way energy comes in. If the work from the surroundings is not tuned to one of these spacings, then the energy can't go into the system and it just bounces off, which is an elastic process. You don't change the internal structure of the system. If this energy is tuned very closely to these energy spacings, so I could have a 2E0 photon come in. If the gamma has an energy of 2E0 and I start in the ground state, that photon can come in and I can go up. If I'm in an excited state, I could also go down, releasing a photon with an energy E0. And that is how everything you've done in chemistry, involving energy levels, photons coming in, photons coming out, is really just a part of the energy principle.